Problem 14.43 states that three spheres, each of mass m, can slide freely on a frictionless horizontal surface. Spheres A and B are connected to each other by an inextensible inelastic cord of length L and are at rest in the position shown when sphere B is struck squarely by sphere C, which is moving the velocity v naught, and it is straight down. I'm going to call x to the right and y up for the coordinate system. And knowing that the cord is taut when sphere B is struck by sphere C, and assuming perfectly elastic impact between B and C, and thus conservation of energy for the entire system, it wants us to determine the velocity of each sphere immediately after impact. So the things that we're given is V naught's a given. Theta is the inverse sine of 1/3. You can see that from the figure right there. L is given to us, and then when you calculate that inverse sine of 1/3, you'll get theta equal 19.47 degrees. That's rounded off. I keep the entire thing in my calculator for calculation purposes. We have conservation of linear momentum in this setup, so we'll start off with initial momentum of the system being, this is mv naught, or m sub c v naught, and it's downward, so it's a minus j. And then after the collision, m sub c, vc in the j direction, because since since c is only being hit in a vertical direction, then it can only have its change in momentum be in the vertical direction. So that's why it's a j there. Then B has a possibility of x components and y components, so that's why I wrote it out that way. And then A, one thing we know about A is it can only be in the direction of theta, so we can write that out as the m sub v sub a times a lambda univector, let's say, in the direction of A to B, which is going to be cos theta I minus sine theta j. If we take a look at breaking this vector equation into two scalar equations, and we look at the coefficients of the I unit vector first, we got 0 over here on the left-hand side. Over here, we got VBX and a VA cosine theta. So there's the equation coming out of that. The J parts has got a minus V naught on that side. You got a VC right here. You got a VBY right there. And you got a minus VA sine theta right there. If we look at the coefficient of restitution for the collision between B and C, E is equal to the ratio of the after velocities to the before velocities, or the negative of the ratio. Anyway, if we take VBY minus VC for after the collision and divide it by VC minus B and VBY before collision, VBY before collision is 0, and VC before collision is minus V naught. And we set that equal to 1 for a coefficient of restitution for perfectly elastic impact. From that equation, we'll get VBY minus VC equal to minus V naught, or we can solve for VC in terms of VBY and V naught. Now what we're trying to do is take our equations, like this equation here, and the two linear momentum equations, and combine them later on with a conservation of energy equation, and we'll have our 4 equations of 4 unknowns that we need to solve for all the unknowns. So we're going to substitute in VC right here into this equation. We'll have minus V naught equal to, and VC is VBY plus V naught from right there. And then VBY is right here, and then minus VA sine theta is right there. So out of this, we're going to have 2 VBYs. That's why the half is appearing in this equation. We're going to have minus 2 V naughts, and that's why just a V naught's occurring here, because we're going to divide through everything by 2, and then we'll have a 1/2 VA sine theta with the VA sine theta over to the left with the V naught. When you simplify that equation down right there, you can get that VBY is equal to 1/2 VA sine theta minus V naught. And then up here, where VBY is equal to this right here, you put it into this equation, and you'll find that VC then is just 1/2 VA sine theta. If we write out our conservation of energy expression, then 1/2 mass of C times velocity of C initially squared equal to 1/2 mass of A equal times velocity of A squared afterwards, and then this is the velocity of B squared afterwards, or velocity of B and then quantity squared afterwards, and this is the velocity of C squared afterwards. And the 1/2 m's would cancel out in all terms because all the masses are the same, so that leaves you with V naught squared, VA squared, and VBX then up here is minus VA cosine theta, so there's minus VA cosine theta quantity squared. VBY squared is from right here, so there it is in quantity squared, and then VC is from right here, and you got that squared. Now they've got an equation that only has VA as an unknown in it. So you simplify these things down, square it out, all those terms right there. Of course, this becomes a 1/4 VA squared sine squared theta minus 2 times 1/2 VA V naught sine theta plus a V naught squared, and then you get your 1/4 VA squared sine squared theta right there. One thing you'll notice is that the V naught squareds right here are going to go away. And we're going to have 0 then equal to VA squared plus VA squared, a VA is going to be canceling out each one of these two. Since VA is in every term after we get rid of the V naught squared, then we can reduce every term by VA. So that's why this goes to VA squared to VA. This goes to a VA cosine squared theta. This goes to a 1/4 VA sine squared theta. This right here, I'm putting it over here because it doesn't have a VA in it. This is going to become minus V naught sine theta. And then this 1/4 VA sine squared theta from right there. When you solve for VA out of this equation, you'll have V naught sine theta right here, divided by all these terms right here, the coefficients of VA, which is a 1 plus cosine squared theta, and a 1/4 and a 1/4 becomes a 1/2 sine squared theta. You plug your numbers in, you get VA equal to 0.1714 V naught, and it is at that angle theta that we calculated earlier. And then you plug that number for VA in right here, and you'll get VC is equal to 0.0286 V naught, and it's positive, which means it's in the upward direction. So the VC comes down, hits B, and then it bounces upward. And then and you plug into VBX from right here, and you plug into VBY from right there, and you get these two VBX and VBY components. When you take the square root of some of the squares, you'll get a velocity that's equal to 0.985 V naught, and the angle is 80.6 degrees. It's a third quadrant angle, and the text in the solution manual they have it as a fourth, but that's incorrect. And VB is supposed to be a vector right there.